start today's lecture with any questions on yesterday's, Tuesday material? Okay, so what we're going to do is we're going to get more into more advanced performance type questions, and then we're going to get into computing arithmetic. So that's where section 2 is going to begin. So in this case, what we've got up to this point is we talked about clock rate, cycle time, what actually is performance, what actually throughput is. And what we're going to now talk about is, these are just generic terms for the overall computer. And as we learned last lecture, that there's different portions of the computer and the data cabinet, how things break down. So we have instruction fetch, we have instruction decode, execute, memory, and write that. Additionally, different instructions take different amounts of time. This is why we learn about the difference between RISC and CISC computers. Sometimes we have to worry about what ends up happening, especially when we get into computing arithmetic in the next section. You perform several additions. Just so you know, you don't have to do that for this class. This is how I know you showed up. And plus I actually know that you guys are doing the effort and don't do the extra credit assignment. Just doing that, you can just beep, and then you just sit there and sleep in the back. So being able to account for how all of these different things affect performance will really strengthen your capability of evaluating the advanced usual system. So what we're going to do here is we're going to start kind of building the complexity of these performance questions. So in this case, what we did last time was we had one computer ran 15 seconds, one computer ran 10 seconds, which one runs faster, and what's the ratio? Pretty simple. So in this case, what we're going to do is this problem, example 1.2, a program runs in 10 seconds on computer A, which has a 2 gigahertz clock. Computer B runs the same problem in 6 seconds, but requires 1.2 times as many clock cycles as computer A. What is the clock rate for computer B? So before we go into the actual solution, what's a potential issue with clock rate and cycle time that we were talking about yesterday? Heat, right? So heat and cost is a big thing, right? Did anybody know actually how the computing clock signals are generated? All right, so the short version, we won't really go into this in too much detail, but you actually have an oscillating crystal, right? And then what you do is you actually create a voltage across it, and these crystals will naturally vibrate really fast. And then what ends up happening is you get this, waveform, and then you use filters to make them into AC or DC waveforms. So that's actually what's ended up happening. So then eventually, if you, for example, if you take a CMOS course, you have to worry about how the transistors are able to create channels. And from there, that actually has the electrons move back and forth between all the different atoms, which the more you move them and the more you condense things, the more heat is created. So in this specific problem, being able to determine the trade-off between amount of power consumption versus runtime. So that's why this kind of problem becomes really useful in being able to understand. So we recall from last class that our CPU time is equal to clock cycles divided by the clock rate. So when it happens is we have our clock rate here, 2 gigahertz. So what is it? What is actually giga? What does that actually mean? Yeah, 2 billion, right? 2 times 10 to the 9, right? So that's what is going on there. And then, so I will actually figure out, I know the amount of time, right? And I know the clock rate. So this is where, when I was talking about stoichiometry last class, here's the scenario. It's exam day. You get to a performance problem, and then you blank, right? Pressure, what do? The reason why I reinforce these equations and reinforce units over and over again is when it happens is you can just write given. You write down all your givens and you write out the unit. And then you write what it is you're trying to find. And then you can see that, okay, well, these are the units I have. This is what I'm trying to find. And you can actually set up the equation yourself in the event that you're in the middle of panicking on the exam. So that's why we're doing it this specific way. So what happens, you have CPU time is seconds, you have clock cycles, which is cycles, and then clock rate is cycles per second. They cancel out, and that's when you get your clock cycles equals time over cycles divided by seconds. So here these cancel out. So you have 10 seconds times 2 billion cycles per second. So we now know that there's 20 billion cycles that is run by this particular computer array. Does that make sense so far? So then we also know we want to correlate how many. I'll get to your question in a second. So actually, what is your question?
What were you canceling out there?
Seconds?
Seconds on top and bottom?
Yes. Because we're trying to find cycles, right? So what do we know about computer A? Right? Trying to lay out everything, right? We know about computer A, we know the clock rate, it's 2 gigahertz, and we know the amount of time it's taking. And we also know that the computer B runs the program in 6 seconds, so we also know the execution time. So it requires 1.2 times as many clock cycles. Okay? So if you know the clock rate, and you know the execution time of the program, you can actually determine the number of cycles for computer A. So the way we're laying the problem out is, I need to find the number of cycles in A, so that way I can use this unit that we know is 1.2 times as many cycles in the problem. And then it'll help me figure out the clock rate for computer A. So here we know CPU time. I know the clock rate and cycles, right? So if I were to write this out, given 10 seconds, and then I have 2 gigahertz, which is 2 times 10 to the 9 cycles per second. And then they would cancel. And then you multiply those together. The seconds will cancel out here. And then you get cycles, which is what we need. I'm sorry, that's what we need here. So I have 20 billion cycles. Now I also know that it requires 1.2 times as many cycles for computer B, but it's running in 6 seconds. So it's running a lot faster, but I need a lot more cycles to do it. Okay, so it's more computationally heavy. So in this case, I just would take this and multiply it by 1.2. So it comes out to 2.4. Yes? Oh, okay. No. Sorry, I thought you had a question type. So when we do that, that comes out to 24 times 10 to the 9 cycles. So now I know the total number of cycles in a given time that take for computer B to execute this. And then, so if I know the number of cycles, I go back to the same equation. I know the cycles. And what am I trying to find here? What are we actually trying to find in the problem? What's the ultimate goal? Clock rate of computer B. Exactly right. Very good. So then I would just take this problem. I would just solve it for clock rate of B. I know the clock cycles now because of how we set the problem up. And I know the CPU time because it's given in the problem. So that just becomes 24 times 10 to the 9 cycles divided by 6 seconds. Right? So that becomes 4 times 10 to the 9 cycles per second, which is just 4 gigahertz. So what's happening is we have a program on one computer and we have a program on another computer. And we have 10 seconds and one runs in 6 seconds. The reason why is because I've increased, I'm running it by 1.2 number of cycles. I actually need to get it to run in order to actually meet these performance metrics. Does that make sense? And as we discussed a little earlier, and I'll get to your question in a second, that there's just running the clock rate doesn't necessarily help everything. You increase power consumption, and then when you get down to the physical details, basically what's without going into too much detail, if you have a transition from a 0 to 1 in a transistor, what you're doing when it's working properly is it has these things called noise margins. So it's like 0 to 0.1 and then 0.9 to 1 is the voltage. And what you want to do is you want it to actually, it's actually going to write. Yeah, there we go. You would get from to 0 to 1 like that. If you run it too fast, it becomes very difficult for the physical, the actual transition to change, and sometimes it won't make it in that very short amount of time, so you actually lose information. So just increasing the clock speed doesn't necessarily guarantee that it's going to work. Okay? So
if computer B didn't require 1.2 times as many cycles as computer A, but still ran at 4 gigahertz, would it complete the program in 5 seconds?
No. Okay, so that's a good question. Let's revisit it. So it's running it at the same. It requires the same number of cycles, but we're just running it at 4 gigahertz, right? So what happens is actually we require 20 clock cycles. So that becomes 20 divided by 6, which sorry, that would be, let's rearrange it, right? So what we're trying to do is we're trying to find CPU time, right? So I know that I have 20 cycles, right? Clock rate is 4 gigs. So it's 20 divided by 4, so that becomes 5. So that would be in an ideal situation where you're able to just step it up, but it's the same architecture. Yeah. So that's a very good question. I mean, they're all very good. I don't want to discourage your questions, but you get the idea. That shows as an engineer that you're putting pieces together and seeing how things work out. Yes.
When we talked about the relationship between heat and clock, I mean, is that the clock rate? That
Yes.
Sort of, okay.
Mm-hmm. Yeah. So power consumption is you won't need to know this equation in this course, 1/2, and so there's something called the load capacitance of a transistor times the supply voltage squared times the frequency of switching, and the frequency of switching is the clock rate. Yes.
I got a load of computers you guys are doing there about to manipulate the clock speed as a user or whatever. Is that basically what you're doing? You're just speeding up your actual cycles?
Yeah, okay, so here's the difference, and I think going into example 1.3 might explain that a little more, so let me scroll up as I'm answering your question. It's not just that, so the number of cycles would be the same if your program runs short, right? So if I speed up the clock rate by a factor of 2 from 2 gigahertz to 4 gigahertz, it's going to cut the time in half, provided that the program actually works. If we're running on a different instruction set architecture that actually compiles a program down differently, remember in last lecture we were talking about there's a correlation between the code and the instruction set. So sometimes, based on that instruction set, you might require a different number of cycles based on the underlying physical details of the computer organization. Okay? So that's why organization and architecture is so important. So in this specific case, in 1.2, what happened is I have a different architecture that requires 1.2 many cycles for a specific program to execute. But because I'm running the clock speed at twice as fast, I'm still gaining a performance improvement. But instead of 5, as you were asking a little earlier, it becomes 6, just because of the trade-offs. Does that answer all the other questions? I think I saw one other hand over there. All right, so example 1.3. Suppose we have 2 implementations of the same ISA, right? So in this case, it's actually the same architecture. No difference in clock cycles. Everything's working the same. Computer A has a clock cycle time of 250 picoseconds and a CPI of 2.0 for some program. Computer B runs it in 500 picoseconds with a cycles per instruction of 1.2 for the same program. Which computer is faster and by how much? So here's how this breaks down, and there's key things. I don't ask trick questions. There's certain details that you want to pick out in there to understand. So suppose we have 2 implementations of the same instruction set architecture, meaning that we're running a program and they're the same ISA. What that means is that if it's on the same instruction set architecture and it's the same program, it will take the same number of instructions. So what ends up happening is, if you recall from your equations, we correlated execution time. We have 2 different execution times, and we're trying to figure out which computer is faster, right? So we have clock cycle time, which is 1 over clock rate for each of these 2 computers. And in order to actually run the programs, the cycles per instruction is 1.2 versus 2.0. So we're trying to figure out which computer is running better. So in this specific case, what happens if I don't remember the equation? I know that I have cycle time is seconds, CPI is cycles per instruction, right? And so it would be cycles per instruction, right? Times seconds per cycle. So if you're canceling these out, we still have seconds per instruction, right? The key detail and why the question is phrased the way it is if you're comparing two instruction set architectures and they have the same number of instructions, what you can do is you can just include a variable I, and then you include it in both the numerator and the denominator, and the instructions will cancel each other out that way. Does that make sense? So that's why this specific equation is set up this specific way. So we're making a comparison here. We don't know which one's working. In example 1.1, it was given in the problem that one of them's running much faster. We're trying to figure out the ratio. In this case, you're given a set of performance metrics with CPI and cycle time, and we're trying to figure out which computer will run the program in a specific way. So in this specific case, we just set it up execution time A over execution time B, and then we plug it in. We have 2.0 of cycles per instruction times our variable I times 250 picoseconds. And in the denominator for execution time B, we have 1.2 times I times 500 picoseconds. And then we cancel out that. And this is a pretty good example of a type of thing that would come up on an exam. So in this case, you can see 250 over 500, right? But if you multiply this by 2, so basically this becomes 1 over 1.2, right? Just so you know, I don't permit calculators on exams. I'm not grading your ability to do, complex mathematics. I'm grading your ability to demonstrate your understanding of the advanced digital system, right? On an exam, but the numbers will come out like this. You'll know you're on the right path if you're doing something that comes out to like 5 over 2 or just 7. If you're getting 6.8173, you've done the problem wrong. That's just so you know. So the problems are going to come out. If you see this, you go, oh wow, that's 2 times 250. That's 500. So and then 1 over 1.2 is a correct answer. I'll accept that for 100% full credit. You don't need to go in there and figure out that it's 0.83, right? Because this 1 over 1.2 demonstrates the understanding, right? Remember, what did we talk about from last class? If we come out with it's 1 over 1.2, which computer is running faster? What does that number mean? If we're comparing two execution times, like we did in example 1.1, and it comes out, and the ratio comes out to be less than 1, what does that imply about the computers? That means the execution time of A runs longer than the execution time of B. That means B is faster. So putting 1 over 1.2 demonstrates understanding. Yes?
Is that an I just for instructions right there?
Yes, it is. Hey, did you have a question?
It says A is faster.
That's okay. That should be B, because B takes less time, right? I'm sorry, they execute. Yeah, I see what you're saying. Yeah, so the 1 over 1.2, this is me getting my performance thing wrong, right? So performance, in this case, so this means that if it's 1 over 1.2 and we're comparing execution times, that means the execution time of B is taking longer. Yeah. And then execution A is taking shorter. So here I say, since it's less than 1, the execution of T is less than B, therefore A is faster. All right. My mistake. Hey, any other questions before we move on to average CPI? All right, so up to this point, what we have covered is what happens if it's just some program, right? We haven't really delved into different types of instructions, right? So we haven't talked about what happens when I have a bunch of addition instructions, or multiplications, or load words, or store words, right? One of the reasons I emphasize in the topical guide objectives about load word and store word and having short register accesses versus non-volatile memory access is because different instructions take different amounts of time. And so in order to figure that out, we use this metric average CPI, where we are trying to figure out the correlation between the summation Here we have the multiplication of CPI of this specific I. So let's say I have 5 different instruction types. We have CPI of I times the number of that instruction plus CPI of 2 times the number of that instruction. And the next example question, you'll see this in detail. And then bottom, we just sum the total instruction count. And that allows us to correlate the number of cycles it would take to execute, a branch instruction versus the number of cycles it would take to do a load or a register type or arithmetic type of instructions. And allows us to formally define average CPI as a unit that may be used when determining performance metrics when there are different instruction types that take different amounts of time per instruction class. Yes?
So this is saying that, like, for different types of instructions, there will be different average CPIs?
Yes.
Okay.
Yep. The next example question will put that into more clarity. But yes, you are correct. It's an I believe button, but only for 30 seconds. All right. So example 1.4. So here's how this breaks down. So we have just 3 generic instruction classes A, B, and C, right? So in this specific case, the CPI, cycles per instruction, for instruction class A is 1. For B, it's 2. And for C, it's 3. So now we're comparing it on two different computers. So let me walk through the formal wording of the question. Given the following CPI for 3 instruction classes and the number of instruction counts for each instruction class on 2 separate computers, determine which of the 2 computers is faster and the average CPI for each. Okay. So the average cycle per instruction, number of cycles per instruction. Here we're not really given a clock rate, so basically whichever CPI is less is going to be our faster computer, right? So in this specific case, we have these 3 different CPI classes, and then we're running them on 2 different computers where they're compiled down in different ways, right? So it's this is where a compiler-driven encoding of the micro engine comes into play. In this specific case, on computer 1, we just have 2 instructions for A. For B, it's 1, and for C, it's 2. And for computer 2, we have 4 for A, 1 for B, and 1 for C. So if we revisit the average CPI equation, that means it's the summation of the CPI of the specific instruction times the number of instructions for that specific one, plus, so we're summing it, so we multiply these 3 and then get the summation, right? And then the denominator is the summation of the instructions, so it becomes that sum, right? So what we have here is the average CPI. Here, for computer 1, we have 1 times 2, which is this one, plus 2 times 1, which is here, plus 3 times 2, which is here. Summarize sum of that, and it becomes 10. For computer B, it's 1 times, instead of white, let's do red, 1 times 4, plus 2 times 1, plus 3 times 1. 1 times 4 plus 2 times 1 plus 3 times 1, and that comes out to 9. So that gives us our numerators for those 2. What happens is, remember, it's the average of CPI times the number of instructions. That's that summation. And then the denominator is the summation of the instructions. So what we do here for computer A, 2 plus 1 plus 2, that gives us 5. So that gives us 10 over 5. Right? So the average CPI for computer 1 is 2. Does that make sense? So likewise, we got 9 for the numerator, and we want to sum up the denominator. So it's 4 plus 1 plus 1, so it's 6. And so that becomes 9 over 6, which is 1.5. So that means because the CPI of computer 2 is 1.5, CPI of computer 1 is 2. In this case, the clock rate doesn't make a difference. They're the same. So if I have the same clock rate and I have the fewer number of cycles per instruction over a given program, that means that specific computer is faster. And that's how I'm pretty confident I got it right. All right, so I know there were a lot of questions about the definition. Does that make, now that we've gone through this example, does that make a lot more sense? Awesome. All right, I'll let everybody kind of finish jotting down for a quick for a little bit. So while you're doing that, I'm going to kind of briefly allude to what we're going to talk about next. I can promise you the definition of Dahl's law is going to be an exam question. So let's break this down. Think about a potential conceptual error that a new engineer might have, right? So I come to you with a problem. I need this computer to run faster. It bothers me, bugs me, right? And I come to you and I say, how are we going to speed this up, right? And you do some analysis and you run the clock rate. You're just like, oh, let's make the clock rate go faster. Well, it consumes a lot more power. For some reason, the customer has figured out that very specific power metric that you have to meet, and it violates it. Okay, well, that's not a solution. So I'm trying to figure out how fast I can improve things. Another way you can do it is to improve a specific instruction type that you think that is commonly used. Remember those 4 rules? One of them was make the common case fast. So you realize in this specific computer that your customer wants that it does a lot of addition or it does a lot of multiplication. This is, for their specific thing, this is something that you really, improving this without having to speed up the clock rate will really help you. And so you're trying to calculate the improvement. What do you think would be a common mistake? Right, well, that's kind of the. I'm talking about like you're trying to evaluate, improve. So now let me rephrase my question. You've made the improvement to an arithmetic logic unit, right? And so the specific arithmetic instructions are improved. And now you're going up in front of your customer and you're trying to justify your improvement. What do you think would be a common mistake in presenting your improvement? Making it too complicated. You're on the right path. So a common mistake is I improve the speed up. So this definition here, speed up, is the factor by which execution time is decreased, and it's found by execution time old over execution time new, or performance new over performance old, right? A common mistake is that they will take the speed up of a specific instruction type and apply it to the whole computer and say, instead of just improving the arithmetic instructions, I've improved the entire computer by a factor of 2. That's, of course, incorrect. And so it's a very common mistake that students make on exams, and it's a very common, it's a less common mistake in industry, but it's a common mistake. You don't want to mischaracterize your product to your customer. So, to combat this, I emphasize this concept of Dahl's law. So, define Dahl's law using an equation and state its importance. That's the problem. If you look on the TGOs on Blackboard, that's the way the problem is phrased. So this specifically, I have my improvement in engineering has affected a certain portion of the number of instructions in a portion of the data path, and I've improved the speed up of that specific portion. But then I have an unaffected portion that I haven't messed with. Right? All of my load word and store words are the same, or something like that, right? And then the actual new execution time is what you've affected plus what you have not affected. If you can convey to a customer, okay, well, we have improved our arithmetic logic units by, our speed up is 1.2, all the load words are the same, so therefore, here is your actual speed up. So it'll be like 1 point, depending on what it is, 1.083 or something like that, right? So that way you're not falsely conveying your accuracy of your speed up of your overall computing system. So it helps in finding the maximum expected improvement to the overall system when only part of the system is improved. Does that make sense? Yeah.
So it's kind of like you're tweaking the software part of what they wanted to do versus the hardware part.
Well, that's one way. Okay, so there's all kinds of different ways. So yeah, so if you are doing a software optimization, you still have to put the software optimization on the hardware. So you reduce the number of instructions. CPI, right? Cycles per instruction, then you multiply it by number of instructions. So in software, you've affected the number of instructions, but the clock rate is the same. The number of cycles it takes to execute that specific instruction class is the same. So yes, you're exactly right. That's one way of doing it. Another way of doing it is how I can affect a specific aspect of the hardware that performs certain instructions faster, but if I still have the same number of instructions, it's not like I'm reducing the number of instructions. Yes?
The reason why I ask is, I know sometimes it's going to operate the system. Windows takes a lot more time to set all the stuff in the background. You're doing industries, Linux, Unix, and stuff like that. It's stripped out.
Yes.
Is that more effective as far as this scenario? If the customer asks, I want to do this, I don't care which program
Right.
I just want to do this, and we can take the Windows and put it on a Unix system that runs 30 times faster. With less time, less cost.
Exactly, and that's how you would justify it to your customer. Say, all right, so here's the key thing. So the question is, how would my understanding of the operating system and the hardware and the software, that big chart I showed you at the beginning of the first class, showing your understanding of how that all ties together allows you to justify to the customer certain improvements. So in this specific case, let's say, and in section 6, to even go more in detail, we're going to be going into virtual machines where we're actually going to be using the non-volatile memory as kind of a cache. And so that ends up taking a lot more time, but allows you to write bigger programs. So, and so if you work with the Java virtual machine, Java, the garbage collection is done for you, and a lot of the compiling you don't really worry about. Like you don't really do pointers in Java, right? Whereas if you're doing it in C++, you worry more about pointers. So there's trade-offs. If I don't want it to be pretty, if I don't have to go into a customer and say it has to look really nice, if I'm doing with industry professionals who really know how to use the Unix command line, like you all will learn when we get into Cadence, all I needed to do is run fast. So in this case, MIPS, the philosophy of MIPS is high execution performance of compiled code. You'd want to do it like that. Yep.
So would making a change at a hardware level typically cost more than on software level?
Well, no, not necessarily. Ultimately, it depends on how much you're paying the hardware or software engineer. But the key thing is being able to, ultimately it's the application, right? So without going into too much detail, let me start, I'll finish up answering your question and then get into these example questions. It ultimately is application. There's no one right answer. So in some cases, using application-specific integrated circuits are the best because you want it to do this one specific thing only, and you need to reduce the cost. Whereas reconfigurable computers, such as FPGAs, you want to make sure that you can kind of load up new software and then being able to, have a robust system, right? So, for example, our laptops, it can run Unix, it can run Windows, because ultimately there's an underlying hardware that is able to operate both, right? So in this case, I'm using Windows. One of the good things about this is I can record the lectures, right? It allows me to use specific PDFs and type everything up. So in this specific case, that's what I'm using. On the Cadence server, where you're going to be running all of your code, we use Red Hat, Enterprise 5, right? Because it's really good. It's a good server. It allows for good communications. We were talking about I/O. So there's no one right answer to your question, but it's ultimately you go through all these considerations, and then if you're going to a customer, or you're going to the specific your boss, and you're trying to justify it, that you justify it by saying, all right, well, these are the trade-offs. This is what's good about it. This is what's not so good about it. But the thing is, based on what our customer wants or what the deliverable is, this is the best solution based on our performance metrics and our deliverables. Right. So let me forgive me for cutting off the questions, but I want to start getting more into these example questions. So here we're actually doing an application of Amdahl's law. So we're given that a performance execution is 100 nanoseconds. So we improve what's known as floating point addition. So floating point addition, we'll get into that in section 2. But basically, that's like addition in scientific notation in computers. So floating point notation, which takes up 20 nanoseconds, we improve it by a factor of 5. What's the new execution time of the program? So common mistake would be 100 divided by 5. It takes me 20 nanoseconds. So using Amdahl's law, we know that we have 20 nanoseconds, and then the speed up of the floating point, we've improved by a factor of 5, which is quite an amazing improvement, but we're only affecting that portion. So 20 divided by 5 is now 4 nanoseconds, right? So now we want to see how the speed up affects the entire program. So we still have 100 minus 20 nanoseconds of unaffected instructions. So it's 100 minus 20 is 80. So we now have 4 nanoseconds, which is after the speed up of the floating point addition, plus the original 80 that we're not messing with at all, and that gives us 84 nanoseconds. So the speed up becomes 100 over 84, not 100 over 5, right? And 100 over 20. Does that make sense? That's why I'm understanding Amdahl's law is so important. So that's a simple result. Here's a more complex problem. And so this is kind of a good way to kind of walk through and demonstrate your full understanding of everything. So this is a good, like, oh, I get to the exam. Oh, okay, let's, I'm panicking a little bit. Let's walk through it together. The table below shows the instruction type breakdown for different programs. So this way, we're just going to do program 1. Using this data, you will be exploring the performance trade-offs with different changes made to a MIPS processor. So in this specific case, we have 1,000 compute instructions. We have 400 load instructions. So we're taking stuff from the data memory and putting it to the data path. We're also going to store 100 times. In this case, we are also doing 50 branches. So branches, like if you're going through you all familiar with for loops, while loops, if statements? So a branch, so if you're doing if I does not equal j, and if I doesn't equal j, go inside the code, right? And if I equals j, you can skip past it. Skipping past it is what's known as branching. So in this case, we've encountered instances where we don't want to do the inside code. We branch to another instruction by improving incrementing that program counter that I showed you before in last class with the data path. We do that 50 times. So you summarize, sum those up, and it's 1,550. So we have 3 different types of questions here. Assuming that computes take 1 cycle, loads and stores take 2, and branches take 3 cycles, find the execution time for each program on a 3 gigahertz MIPS processor. So we know that we have number of instructions. We have cycles per instructions. We have cycles. And then we have cycles per second. So if I'm in an exam and I'm freaking out, okay, so I know I got cycles, right? And I know I have cycles per second, and I know I have number of instructions, right? So I start listing those out, INSTE. So I have cycles, and then I have cycles per second, right? And I'm trying to figure out how to make those. Oh, cycles per instruction is CPI. So that allows me to, then I multiply the numbers of instructions. So here I have 1 plus 100, 1 times 1,000, right? So I have the number of cycles per second. So I have cycles times instructions, right? Divided by, and so it cancels out, and then we'll get number of seconds over here, right? So 1 times 1,000 plus 2 times 400 plus 2 times 100 plus 3 times 50. And we divide that all by 3 gigahertz. And that comes out to 2,150 times 10 to the negative 9 seconds. So that's more of a more complicated thing. If it starts adding up and you get weird numbers like this that don't intuitively cancel out on an exam, that's a sign that you're a little off track. But this is just giving you an idea of how these all tie together. Right, so that's part 1. So you just put those together using that knowledge. So part 2, we have the same numbers, compute, take 1 cycle, load, and take 10. And I'm sorry, that should be 2, right? Yeah, it's still 2. Forgive the typo. And branches take 3 cycles. What is the speed up of a program if the number of compute instructions can be reduced by 1/2? So somehow we have done a compiler, a software improvement, right? And where in this case, instead of requiring 1,000 computations, we only need 500. They're reduced by half. So the simplest way is to just take the same thing here and divide it by half, right? So instead, so I put the whole equation. So what you could do is simply just say divided by 2, 6, 500 away. So this would be, 500 plus 800 plus 200 plus 150. We don't affect the clock rate at all. So that adds that up, and that just becomes, as you see here, the subtraction of 500 comes out there. And then you just compare there, what's the speed up? 2,150 divided by 1,650 comes out to 1.3. Right? And then, oh no, so there's no part C. Part C is the next has problem. All right, so you see how you're starting to put these pieces together, and you're seeing that, okay, so Amdahl's law affects performance in this specific way, because we have to worry about different instruction classes, because there are certain levels with hardware and software. Right? I saw your hand up. You have a question? Sure. Okay.
Oh yeah, when we give our answers in seconds, do that like a specific way.
Well, I put that there specifically. I mean, the key thing is, box your answer, I guess. Obviously, okay. So here's the thing. When in doubt, my philosophy on grading is give me a reason to give you points, right? So show your work. And let's see. NWNC is a common thing that I'll put. So on an exam, if you see NWNC, that means no work, no credit. So think about it this way. I come from the Naval Nuclear Power Program, right? Like I talked about in the video. Okay, so if I get lucky and put the right answer into the reactor, does that make you feel any more comfortable? Right? So it's the same thing. When you do things in engineering, sometimes you're going to be put in positions where people's lives are going to be at stake. So you want to make sure, don't just lucky guess the right answer. You have to demonstrate that you show understanding in order to be part of the engineering practice. So another one I'll put is like right answer, wrong reason. Right? So sometimes people will somehow have the right answer, but the justification is nowhere near correct. But so basically do show your work, right? So I'm not guessing if you put if you just write 1.3, okay, that's sure. But what does that actually mean? Does that kind of answer your question?
Yes.
Yes.
So here we've what we've done is like we've sort of redone the equation in its entirety instead of using the affected over speed up plus affected.
Yes.
Execution time. So this is like sort of a way around using that second equation kind of.
But you are using it in a way, right?
Okay.
So the key thing is the equations as they're initially presented. I'm going to scroll up to 1.7 as I'm answering your question. But the important thing to remember is that the computer is broken down into different parts. Right? So Dahl's law is kind of taken here, right? We're we're summing it, and then we take into the number of equations. So the way that you're applying your knowledge there is, I understand that by speeding up the floating point by half, I'm not, it's not just 2,150 divided by 2. Does that make sense? So you're demonstrating that you understand that the program, specifically the program and how it's being implemented in the advanced control system, is affected in a different way.
Okay, so using the 1,000 instructions over 2 is sort of like the 2 using the speed.
Yes.
Okay.
Yeah, the 2 is the speed up. Yes.
Gotcha.
Mm-hmm. So the number of compute instructions is reduced by 1/2. That means my speed up is 2. Any other questions? All right, excellent. So 1.7. Here we're going to a type of specifically this question. It's part A addresses a common conceptual error that I think will become very helpful. So for 1.7, give the following table shows the instruction type breakdown per processor of a given application executed in different number of processors. Right. So here we have floating point instructions, integer instructions, load store instructions, and branch instructions. So in this case, then we have the CPI for each instruction type, right? So now I know instructions, I have CPI. Automatically, without even reading the questions, you can think, okay, I can calculate the number of cycles, right? So part A, how much must we improve the CPI of floating point instructions if we want the program to run 2 times faster? So your boss comes to you and says, all right, in another research group, we've figured out how to improve floating points. How much do we need to get the whole program to come down by a factor of 2? So then you go this equation. What's my whole number of cycles, right? So I've broken this down into more complexity than I would require in an exam because I want you to see all the detail here, right? So floating point instructions have CPI, plus integer instructions have CPI, there's integer instructions, and likewise for all of them. So you multiply them all out, and you get 8,192 cycles. Okay? And so I did a little proof here, but here's the key detail. I'll go over the proof in a second. Notice how the total number of cycles for floating point is 560 times 1. And I need to reduce the entire program by half. Okay? So half of 8,192 is 4,096. So exactly, which means, I heard you all whispering it. Not possible, exactly right. You only have 560. So therefore, since floating, and that's what this whole thing here. So floating point instructions do not consist of half of the instruction cycles. 560 is less than 4,096. Then this is not possible. So then you go to your boss and say, hey, based on this, I've done the math. What you're asking for, it can't happen. Okay? So basically, what I was saying here is I broke down 560 minus x. How much could I reduce it by, right? And so that's how the question is phrased. So I would say, here's the number of cycles, and then basically what I've done is I've solved for x, and I came out with this very large negative number. Right? So not only I would have to be able to get like Doctor Who and somehow get a TARDIS and take back instructions. Yes?
Could you recognize that there's only 1 cycle per instruction for the floating point, and you can't do less than...
Yeah, if you multiply 560 times 1, and you say, all right, so the whole thing's 8,192, I need to get 4,096 cycles back. So no cycles per instruction. This is the number of instructions, this is the number of cycles, right? So cycles have CPI times the number of instructions gives you the number of cycles. Okay? So in this specific case, I have a program that's working. I know the number of total number of cycles. In order to get speed up, I have to cut the number of cycles in half. In this case, 560 times 1. Okay, so the answer to your question is no. I see what you're trying to ask. No, not looking at 1 is not it, because what happens if this was 5,600 times 1? And it still came out to 8,192, right? So what that means is 5,600 is more than 4,092. So then I would actually try to, I say, okay, well, I need to take out 4,092. That's what part B is, right? So working through, I'll clarify your conceptual error by working through part B. But in short, no, because you have to get the total number of cycles. And that's not this is cycles per instruction. And this is why it's actually a good question about why Dahl is important. Because the cycles per instruction for this specific instruction, 1 plus 1 plus 4 plus 2, that's 6 and 8, right? But in this specific case, if I worked it out in a different way, whereas if it was 5,600, it would actually constitute of more than half of the cycles required to execute the entire program. And as a result, you could do that. So just saying it's 1 isn't justified. All right, so and to provide clarity even further, let's do part B. But you're understanding it, getting the concept stuff. If as I say to the next slide or the next scroll down, if you're asking that question, that means you're understanding it. So that's a good sign. All right, so by how much must we improve the CPI of load and store instructions if we want the program to run 2 times faster? So in this case, load and store is 1,280 times 4, right? So in this specific case, it comes out to 5,120. So we know that's larger. So we do speed up. I want the number of cycles that I need to have remaining. So I've worked this equation out. So in this, how much must we improve the CPI? Right? So I need to get the number of cycles down. So it's not asking for, I need to reduce the number of instructions. I need to reduce the CPI in this specific problem, right? So here's what I did. This is kind of a simpler version. So I know, here's the number of, we use our speed up equation, or performance. So we have an initial minus the number that I need to reduce by. So in this case, we figured out that if we remove 4,096 cycles, we will cut the execution time in half, right? So in this specific case, in order to reduce, it's 5,120 minus 4,096 divided by 5,120. And the reason why I'm doing this is because I have the number of instructions, right? 1,280. And then the CPI, the initial one's 4, right? So 4 minus 4 minus x divided by 4. That's how I'm able to actually figure out what the final answer is, right? So what's going on here is I solve for x, and x becomes 3.2, right? So what this means is, how much must I reduce the CPI to get it down so this works out? So when we figure this out, it's 1,024 is the result of 5,120 minus 4,096, right? And then what ends up happening is, if you divide those out, so if you multiply both sides by 4, it cancels them out. So what ends up happening here is you solve for it. This is the result, right? Does that make sense? The key thing is, I'm not going to give an example, a question like this on the exam. What I want you to do is it's more of a mental exercise. I want you to kind of walk through what's going on. Okay, so I need to improve the cycles per instruction. Go back to what you're talking about, hardware versus software. So in this specific case, the software, like, we can't improve the number of instructions. How much do we need to improve the CPI by? So now we're going into what can the hardware do. So here, I solve for x, and x comes out to 3.2, right? So what ends up happening is it must be reduced. That's the way the question is phrased. So I have to get rid of 3.2 out of 4 to reduce it that much. And intuitively, that makes sense because I'm bringing 5,120 down to 1,024. So it should be a really significant percentage of the number, right? So if you're coming out as like 0.2 over 4, that's really low, so the math doesn't work out. So in this specific case, 3.2 divided by 4 comes out to 0.8, which is 80%. So even if you're doing the problem, sometimes, okay, so the problem's working, and this is why we're going to do part C, is we're going to come up with a different solution that's actually more feasible. So then you would go back to your boss and you'd say, all right, yes, it is possible, but you're asking me to get an 80% improvement in the cycles per instruction. That's really, really difficult. Like I'm going to need a lot more funding. And I go, okay, well, but you've shot down both of my last two ideas. All right, you're so smart. What's your next thing, right?
So what do you say multiply both sides of 4 cancel out?
Oh yeah, so all right, so basically, what ends up happening is if you're doing 5,120 minus 4096, right? So that comes out to 1,024, and you have these values here, right? So if you do the math, it works out. So basically, it's short version put into a calculator. All right. Sorry, because I do want to consider. If you put in, I just want to put that up there to explain the answer. All right. So part C. All right. So we analyze the full data path and we come up with a slightly better solution. So if I reduce the CPI by 40% of integer and floating point instructions, and the CPI of load and branch by 30%, how much can I improve the instruction, the speed up by, right? So in this case, instead of 1, it's 0.4. Instead of 1, it's 0.4. So we had this initial one, we had 1, right? So 40% of 1 and 40% of 1 there, right? Likewise, we have 30% of 4 and 30% of 2. So then we take this and we get down to 2,713.6. And then we just say our speed up is 8,192 divided by 2,713.6. And that comes out to pretty much 3, right? So instead of saying, all right, I need to get a huge speed up in one area, or I need to almost completely get rid of all the cycles, how about let's make smaller improvements throughout the data path? This 30% is reasonable here. This 40% is reasonable here. Instead of getting 80% in one area. And they go, oh, you're pretty smart, right? And so instead of getting half, instead of speed up 2, I got a speed up 3. Even though there's not one single instruction that I got a speed up of 2, right? So even at the best, it was only 40%. But if you're doing it throughout the entire data path, throughout the entire instruction set, because you're reducing the number of cycles per instruction, particularly of the load store, that's where you're gaining a significant improvement. Okay, so does that clarify all of the? Right, so that's where kind of how all of Amdahl's. So this is kind of a very complex type question. The type of question I would ask you on an exam is: Engineer 1 comes to you with this improvement. I'm improving the clock rate. Engineer 2 comes with you an improvement of improving the data path in these two stages by a certain amount. Figure out which engineer's solution is better. All right, so on that note, going to arithmetic for computers. Right, so we've talked about performance, how we can get computers to run faster. Now we're going to start getting into actual how these computational arithmetic takes place. So I actually included this quote here from the philosopher Thomas Hobbes. He actually said this in 1656. So what he was talking, a lot of philosophers like Pythagoras was also a philosopher. And so a lot of things that they came up with back then are still applicable now. Right? So by By rationation, I mean computation. Now, to compute is either to collect the sum of many things that are added together, or what remains of one thing that is taken out of another. And so what he's referring to there is multiplication and division, right? So if you're multiplying 4 times 3, what you're doing is 4 plus 4 plus 4, right? And then likewise, if I'm doing 20 divided by 5, what I'm doing is I'm figuring out how many times I can subtract 5 from 20. See, so basically what he's doing is adding the philosophy here. So if someone wants to call it multiplication and division, that's fine. It's really just adding a lot and subtracting a lot. That's the short version of what he's saying. So, are you all familiar with the concept of arithmetic logic units? A little bit. Okay, you know enough to know that arithmetic and its lot. You know what a unit is. You know what a logic is. You know what arithmetic is, right? All right. So, what is going inside arithmetic logic unit? So it's a functional unit where you have 2 separate inputs, a set of control signals, and a result on the output, right? So the values from the registers. So in this case, we're doing add. Remember that example I gave you last lecture where we had 2 different registers, and the value goes into the ALU, and then we have some sort of control signal based on the values from the opcode, right? You kind of remember. It's okay. It's first week of the semester. The control unit tells me whether or not I want to add or subtract or do and, nor, all the different stuff. The registers are the values that I want to actually do the stuff to. And so I don't want to just add other stuff that I want to add 2 plus 3, for example. And then the registers on this output over here, I still want to make sure I'm saying this into the microphone and can be heard. So you have the register values coming in. This tells me what I want to add, right? So I have my opcode and my addition, right? So based on those, something happens in the data path, and we'll go into more detail later. From now, I believe button. And then the register values go in, and then something happens, and that's what we'll learn in this section. And then the value, we want to put it into a register as well. And then we're going to learn about overflow flags today too. So what happens if the values that I put in are too big to be handled by this specific instruction? So remember in last lecture I talked about how risk is a fixed length. So what we're going to talk about in the first topical guide objective is what are my maximum values that I can have here, right? So the range that you can represent in a 32-bit value where you also have the sign bit, right? So the 0 and 1 here, 0 is positive, 1 is negative. And so what we're doing here is talking about the maximum values that can be represented positive and negative without working with floating points. And so in this case, if it's positive and all the values are 1, that becomes 2 to the 31 minus 1. So that's the maximum positive number that can be represented. And then likewise, by using 2's complement, we have a negative number, and it's all zeros. That is represented as negative 2 to the 31st power. So we can represent any number between those 2 values. So that's the maximum range. And then if we want to go above that, that's where you start worrying about floating point. But first, the most significant bit, which is the bit to the left here, is used to represent the sign of the number. So that's topical guide objective 2.2. And so while you're all writing that down, I'm going to just show this example. So what happens is because we're doing it in 2's complement, if we're doing 4 bits, right? So if we're having 0 and then we're doing 7, right? Likewise, when you do 2's complement, so we have the 1 here for the negative bit, you'd flip all the bits and add 1, right? So in this case, because it's 6, it'd be 1, 1, 1, 0, right? And then you flip all the bits and add 1. So in this case, and everything else with bit extensions is going to be adding 1s here, right? So it'd be 1, 0, 1, 0, right? So that's the short version. As you can see, we've done the sign extension for the rest of that. Does that make sense? And so you add those together. And it comes out to 1. And that makes sense because 7 minus 6 is 1. And so that's how you do the 2's complement. So I think you're all familiar with 2's complement from 235. Excellent. All right, so what ends up happening if I add 2 to the 31 minus 1 plus 2 to the 31 minus 1 here, right? Actually, you know what? We don't even need to make it that big. It's 2 to the 31 minus 1, and we add 2. So in this case, we're adding 1, 0 to this number up here, right? So this becomes 1, this becomes 0, carry, 0, 0, 0, 0. We carry the 1 over here, it becomes 1. Right? So we end up getting a negative number. So that's what's known as overflow. And we formally define overflow here as what occurs when the result of an operation cannot be represented with the available hardware. So in this specific case, we have a 32-bit value. Because of that carry that's gone into the most significant bit of the signed value, it's changed, and as a result, we can no longer represent that. So what we're going to do here is we're going to formally define the 2 instances when overflow can occur mathematically and when it can occur mathematically based on the physical details. So that becomes very useful to know. So when you're adding operands with different signs, overflow cannot occur. Why do you think that is, other than what I've written up there? You're adding 2 values of different signs. Yeah, subtraction, right? So if you have a bowl full of water, right? And you're subtracting means you're taking some of the water out. It's not possible for it to overflow. So likewise, if you're either taking out and just keep taking more out, but you need more water than you're trying to take out of the bowl, that's kind of an opposite overflow, right? Whereas if I'm taking 2 positive values and I'm pouring more in, that's where you're going to get overflow as well. So if it's adding operands of the same sign or subtracting numbers of different signs, right? So I need more out of the bowl than that's there. It's kind of negative overflow, so it becomes empty, right? So subtracting 1 from 2 to the 31 minus 1 using MIPS. That's an example of this. You can't get overflow because you're just subtracting, right? So then, likewise, adding 1, and that was an example I gave you, it comes out to negative 2 to the 31, which is not the value we want. 2 to the 31 minus 1 plus 1 should not be negative 2 to the 31. Okay. Yes?
For the bit that's determining the positive or negative, it would have to be this length.
Yes.
32.
So remember we were discussing last lecture about RISC data paths? So RISC data paths, that's what we're going to be studying in this course. They're the amount of information, the word length is 32 bits. In this case, it's fixed. So it's going to be fixed at 32. Now, if you wanted to do something different, that's when you start using CISC computers.
Why do you talk about 32 bits when isn't it obsolete now?
It's an introductory data path. Yeah. Well, actually, let's see. So we got 6 minutes. Maybe it's in this section. Maybe it's in a different section. Okay, it's in a different section where I have the. I will tell this story. Are you all familiar with the video game Civilization? Yeah. So if you're familiar with Civilization, you're familiar with the Gandhi bug, right? All right. So for those of you who do not know what I'm talking about, the whole idea of Civilization is that you pick somebody, a historical leader, and then you try to run the world or build this civilization, right? So one of the players you can be is Gandhi. And so Gandhi, they have an aggression value, which they stored in an unsigned integer. Right? I'm sorry, well, yeah, no, they signed it in an assigned integer. and they want him to be the least aggressive person, so they gave him a value of 1. If you create a democracy, it reduced your aggression factor by 2. They put instead of so you want to say -1, right? So that's what you think would be happening. Is even really unaggressive, except they didn't understand the underlying computer architecture, and they put it in an unsigned addition. So they put in an unsigned addition, and they ended up getting 2,255 in an 8-bit architecture. So that's even though it's a little obsolete with 8 bits and 32 bits, it's now 255, which means Gandhi is now the most aggressive person you can possibly be. And then I have these captures in a different slide set, but basically it's Gandhi saying, "Hi, I'm Mahatma Gandhi, and I'm greeting you with nuclear weapons." You know? And so that's what happens when you don't really understand. So that's where the glitch came from. So it's actually a misunderstanding of how signed and unsigned addition ties together in understanding the computer architecture. So, yeah. So it's really funny when it's a video game, when it's a safety system that's monitoring whether or not the brakes work. You're sending your family out to the grocery store. It's a lot less funny. But you get the idea. So that answers why. Okay, so it's a 32-bit, and you don't really do them anymore. However, of course, if you would like me to make a more complicated data path for you to study in the course, suddenly it's not so much. Yep. It's a good mix of it's small enough to be able to teach to sophomores, while simultaneously the same concepts can be extrapolated to a 64-bit architecture.
What's past 64-bit?
Whatever, like 65. So there are 128-bit architectures. Often that's in CISC or what's known as very large instruction word. So it depends on how many numbers you want to represent. And forgive me for not going into too much more detail yet. When we get into data path design, everything about that will be much clearer. So.
Isn't there like a supercomputer on?
Yes, there is. Yes, there is. So a lot of the research groups use that for that. Okay, and actually, as 2.4 is a good place to stop, so we'll get into floating point with 2.5. So the homework assignment 1 with 2.4. So exceptions. An unscheduled event that disrupts program flow. So we were talking about operating systems, right? So it's not just that I need to know that there's a flag, and it's not like the program's going to go, okay, well, you have bad data. Okay, your program's just going to keep running now, even though your data is wrong. No, that's what ends up happening with an exception. Right? The exception we define as an unscheduled event that disrupts program flow. So it says, oh, hey, you got an overflow. You can't represent the data based on what you're doing. We need to stop the program now and modify it in real time in order to actually make sure it's running properly. So the exception actually, and I'll start kind of pick up on exception at the beginning of next lecture because I want to go into more detail about it. But it stores the current state of all the registers, puts them in there, and then shoots it up to the operating system. And we'll actually learn about that in section 5 about how that's done. But that's kind of the general idea. Important thing, you all ever gotten the blue screen of death, if you're familiar with it? And you see these like 0x and it's a bunch of hexadecimal numbers. That's what these registers are. It's actually saying, sometimes they say what the specific error is, so it'll tell you what the actual error is. And it'll tell you where the current state of the program was stored at the time of the crash. So that's what all that gibberish on the blue screen of death actually is. So on that note, it's 10:45. You're dismissed.
Wait a minute.